Okay, we're recording to the cloud, which will make it easier for our webmaster to then download it.
Okay, so tonight we are honored to have Dr. David Kimbrough with us to speak about drinking water quality. Dr. David Kimbrough is the water quality manager at the City of Pasadena Water Department. With more than 3 decades of experience, he brings a wealth of knowledge and expertise to his field. Dr. Kimbrough has dedicated much of his career to advancing water quality standards and protecting public health in California. Considered a leading expert and advocate on matters of laboratory accreditation and standards, Dr. Kimbrough has helped bring about significant reforms and improvements to the water quality field across the state. In 2019, he was presented with the Excellence in Water Leadership Award by the Association of California Water Agencies for his many years of leadership and service to the California water quality industry. Please welcome Dr. David Kimbrough.
Hello, thank you for that very nice introduction. So I'm going to give a talk on setting, it's called here, Economic Feasibility, Affordability, and Setting MCLs. And this is a topic that is one of constant interest to those of us who are in the water industry and everyone else as well. It's actually, I was actually asked to give a presentation on this very topic in April of this year coming up. So this was convenient that I could now put this presentation together. So let's just jump into it. I have quite a few slides and I will go through them briskly so that we can stay on time. So I'm gonna, there we go. So this is a brief outline of what could we regulate and what versus what should we regulate? What is the risk, and then how do we manage risk? You can't get rid of risk. Risk is just part of life, but we do manage it. So really quickly, we're going to go through risk assessment as the first step of this process, and then risk management, and we'll go from there. Now, I start off with a slide that you don't panic. There won't be a test at the end of the presentation. No one has to memorize this or ever look at it. But I do want to show is this is actually a complicated subject. So you'll notice that there are state MCLs and federal MCLs. And they're not this in most cases, if you look, that most of them are the same. And this is not a complete list. This is just the first 8 of a very long list. Some of them are
MCLs are, what are MCLs?
This is right across like maximum contaminant level. So I'll get into that in detail. I'm just sort of, putting out, recognizing that this is a large, complex field of discussion. And I just want to show you that the numbers, that there are in fact 2 sets of MCLs often, not always. Now in some cases, California has an MCL and the federal doesn't. In some cases, the numbers are the same. Most cases they're the same, but in some cases they're not. So when the US EPA sets an MCL, they start with what's called a contaminant candidate list. And they go out and look for chemicals and microbes that might pose a risk to public health. And they're required every 5 years to come up with at least 5 candidates. And these candidates have to be assessed to determine if they should be regulated. And the process is called regulatory determination, which is a pretty straightforward description of what actually goes on. So does the contaminant have an adverse effect on human health? Now, since this is a drinking water MCL, we don't care about animals or plants or anything else. If we were in the wastewater world, we're worried about ambient water, that would be a different situation. But because this is drinking water, we're only concerned with human health. Is the contaminant known to occur, or is there a substantial likelihood the contaminant will occur in public water systems with a frequency and at levels of public health concern? And so the administrator of the US EPA, whose sole judgment this is vested in here, a regulation will determine if there's a meaningful opportunity for public health risk reductions. So this is really the fulcrum on which everything turns. If we regulate compound X or organism Y, will it improve public health in a meaningful way? So one of the ways they make this assessment is they have what's called the unregulated chemical monitoring rule, where say, okay, we have these chemicals on our candidate list, or sometimes not chemicals, it might be microbes. And so communities, community water systems, public water systems have to go out and test for the presence of these analytes. You might look in wells and lakes and rivers. Most of these will be, you would be looking at a source, like a well, is, PFAS, perfluorinated alkyl substances, present or they're not present, and what quantity are they? But occasionally we don't look in there, we look in the distribution system. Maybe if we're worried about lead or something else like that, we might look at the water as it's in the pipes after it's already been pumped out of the ground or pumped out of a lake. And then they're required to use only accredited laboratories using approved methods. So so if they've decided now, they've made a regulatory determination, so we have to regulate the stuff. So the first thing they do is set a maximum contaminant level goal. The MCLG is the maximum level of a contaminant in drinking water to occur with no known or anticipated health effects can occur. Now, for the EPA, the US Congress set this in their law, says if it's a probable carcinogen or a microbial risk or radiological chemical, the MCLG will always be 0. Makes things easy. Because the United States Congress decided that no amount of these chemicals was acceptable. Lead is not a known carcinogen, it's not a radiological, it's not a microbe, but yet it also has an MCLG of 0. Now, so the hands for the non-carcinogens, the MCLG is based on what's called the reference dose. And so what EPA does is they look at human and animal toxicological studies, epidemiological studies, and they try to make sense of it all. I'm not going to even begin to try to explain the process. It's really complex. And quite frankly, there's a fair amount of subjective professional judgment required. But suffice it to say, they go out and examine all the literature available on these topics and try to come up with an assessment of what would be the lowest concentration that have no known or anticipated health effects. So I'm going to use an example of chromium-6. I'm sure you've all heard of that chromium-6, I would think so. There was a whole movie about it, Aaron Brockovich. It was a subject of considerable debate in Los Angeles County for quite some time. The legislature passed laws on this. So on the federal level, the US EPA looked at chromium. And there are 2 forms of chromium in water. One is chromium-6 and the other is chromium-3. And they looked at this and they said, well, yeah, chromium-6 is a carcinogen when you inhale it. So people who manufacture chromium-6, people who use chromium-6, in the past have historically had increased risk and occurrence of lung cancer. So it is a known human carcinogen by inhalation. But it was their determination that if you were to drink it, your stomach would have enough reducing capacity and low enough pH that it would convert it all to chromium-3, and so basically it'd be non-toxic. And so they have a very high MCL. It's 100 micrograms per liter. It's 100 parts per million. I'm sorry, billion. And so the MCLG is actually equal to the MCL in this case. So that's 100 parts per billion. California, on the other hand, they don't have an MCLG, but they have a public health goal. But it's the same idea. You find the lowest concentration of whatever chemical or constituent, and you find the one that would have the least health effect. pHs are never set at 0. They always have to have a numerical value greater than 0. They also look at the human and animal toxicological and epidemiological studies. They do go through this as their own process. And so what happened in California, unlike the feds, is they said, okay, yes, it's a carcinogen by inhalation. But they said, well, there's a sensitive subpopulation, which may not be, their stomachs may not be able to reduce it all to chromium-3. And so they considered it a carcinogen by the oral route. You drink chromium-6, you might get stomach or intestinal cancers. And so they set their pHG at 0.02 parts per billion. That's a 5,000 time difference between how the US EPA assessed the risk and how California EPA set the risk. And there is not currently an MCL for chromium-6 in California. We are just enforcing the federal MCL. And we'll get into a little bit of this a little bit later on. So we figured out the risks. EPA figures the risk for chromium-6 is 100 parts per billion. California thinks it's 0.02 parts per billion. How do you manage this? Well, the US EPA sets the MCL as close to the MCLG as is technologically and economically feasible. And the specific language is, maximizes health risk reduction benefits at a cost that is justified by the benefits. So they're basically doing what's called a cost benefit analysis. So you take all the costs. So if you want to remove Chrome 6, you got to treat it. You have to be able to analyze Chrome 6. You've removed Chrome 6, then you got to dispose of the Chrome 6. And then someone's got to administer this whole program. And you assign a dollar amount to each of these activities. So everything is denominated in dollars. So this is a Chrome 6 treatment plant in Glendale, California. A lot of their wells have chromium 6, and they actually built a treatment plant. This is what it looks like. This is Pasadena's laboratory. It's not Glendale's laboratory, but you get the idea that someone has to be able to analyze all these samples and determine that you actually removing the chromium 6 and assess the waste disposals, make sure you're getting progress properly. And then you have to have the stuff hauled off. And one of the things that's interesting about many of these removal processes, you don't just remove Chrome 6, you might also remove uranium or something else. And then even though your intent was to remove Chrome 6, you end up instead of just the hazardous waste, you end up with radiological waste as well. So that will impact disposal costs as well. Now the US EPA assesses benefits. So have you improved taste? Have you reduced corrosion? Have you reduced the need to boil water, bottled water, purchase filter? Did you reduce morbidity, adverse health effects, or mortality? These two are now all can be denominated in dollars. Now, again, no test at the end of this, but what the US EPA does is they have calculated using an equation like this, that the value of a human life is $9.1 million. So if you avoid a cancer death by removing chromium 6, that is $9.1 million of benefits. And there's various ways you can assess, put the dollar values in the equation before. You can look at risk avoidance versus compensation. If you have a hazardous job, how much extra pay do people demand to work at that job? Things like that. So you look at inflation and income changes and latency. It's a whole complex system. Suffice it to say, they reduce it all to dollars. One of the interesting things is, we were discussing this before the meeting started, is every human life valued the same? And if you look at that previous equation, it should suggest you shouldn't. That, someone who's over 60 like myself, I only have expected on average to have another 20 years of life. So my life should only be worth a quarter of, say, a newborn baby's.
And I'm trying to do it now. It's a Zoom thing I was going to watch.
So, so the question is, so if you were to assess the value of my life at 60 plus, would it be valued the same as a 1-year-old child's? And in this case, let's say the child's unlikely to get cancer, might get typhoid. Typhoid used to be a major cause of death among children. So ideally, you would then come up with a curve like this. If you look at the bottom of this curve, it's got concentrations of Chrome 6. And say, well, let's suppose we had a MCL of 100,000 or 10,000 or 1,000. As you lower that number, the cost of treatment, cost of compliance, which includes cost of treatment, goes up and up and up. But you're also increasing the value, the benefit of the MCL, because you're avoiding cancer deaths. At some point, these two lines match, and that's where you set the MCL. That's where the costs and the benefits are equal. Pretty straightforward. Now, a lot of people do not like this approach because basically this is what you're doing. You're saying, okay, here's human health, here's human life, and we're assigning values and setting the MCL and protecting human health based on dollar amounts. Not surprisingly, at least not to me anyhow, California has a completely different approach. Now, because I mentioned before, California does not generally set their own MCLs. They usually only do it where the feds have not done it. But Chrome 6 was one of these. They actually did come up with an MCL a few years ago. So the state legislature said, well, the department, this being the State Water Resources Control Board, shall consider the public health goal, shall consider the US EPA's national MCL, and shall consider the technological and economic feasibility of the MCL. And so there's all this long list of things that they shall consider. But nowhere do they say anything, benefits have to equal costs or anything like that. It's very subjective, and without, it's really not very clear. I'm sorry, but it's not. So this is an actual table out of the MCL regulation, and you can see they did number of sources affected. This is just one table out of many. So there's annualized capital costs, there's annualized operation and maintenance costs, there's monitoring costs, on and on and on. And you see there's different concentrations for different MCLs on surface water versus groundwater. Just pages and pages that those engineers up in Sacramento put together to set an MCL. So at the end, they piled all these tables together, cost, and then they set the MCL at 10 parts per billion, in this case, 0.01 milligrams per liter, because they believe that would avoid 12 theoretical cancer cases. They didn't actually say cancer deaths, they said cancer cases, but to make the thing apples to apples, we can consider the cancer deaths. The question then, though, is why did they choose 12 to avoid? Why not 1 or 10 or 100? It's never really explained. And then also, what does this have to do with economic feasibility? The state law says it has to be economically feasible, but there's no discussion of that. It's simply a list of costs. So what happened was the state adopted this regulation, and there was a lawsuit. And I don't want to get into a long legal discussion, but the plaintiffs argued that they never actually looked at the economic feasibility. And basically their argument was that, I'm sorry, let me skip this. The argument that the plaintiffs made was, it wasn't that the department made a bad economic analysis, they didn't make one at all. And the judge agreed. And so they were saying, well, what does economically feasible mean? And the judge was pushing them on that affordable as an issue. And they said, well, economic feasibility is not the same thing as affordability. But the judge pointed out, and this is the ruling of the court, is that it's hard to conceive of economic feasibility without at least considering affordability. It has to be a part of the solution. So now the court has thrown out the MCL and has told the state board, if they're going to make a new MCL, they have to consider not just economic feasibility and technological feasibility, they have to consider affordability. So that's the next step. And they have not addressed that yet. So I'm going to go a little bit beyond. I could stop right now and say, this is how California does it. This is how the feds do it. And that's how this is the math, and that's that. But I do want to go a little bit beyond this, because as the court has made clear, that this is an ongoing issue and that needs to be addressed. So what is technologically feasible? Well, is there a treatment process available to remove, in this case, in the example we're using, chromium-6? Is there a method you can analyze it down to? And there are disposal options. Now, I should point out that it has been the case in some cases where the MCL is set based on the ability of laboratories to measure the match chemical. So there's a chemical called carbon tetrachloride. The MCL is set because at the concentration that it is, because laboratories can't measure below that. If we had better analytical methods that were widely available, the MCL would just be lower for that one reason alone. It's not because of treatment costs or something like that. So the question is, like as I mentioned before, so we have all these treatment costs. The question is, are those costs affordable? Even if they're technologically feasible, are they economically feasible? Affordable to whom, though? Affordable for what? Affordable for when and where? This sounds a little bit tongue-in-cheek, or perhaps a little bit ironic, but these are actually real questions. I would suggest, and this is just my personal point of view, that not all uses of water are equal. Potable water delivered by public water systems is used for a wide range of things. We water our plants with it. We fill our swimming pools with it. We water our terraria and aquaria with them. But MCLs are set to protect human health. They're not set, as I actually mentioned earlier, they're not set based on the needs of plants or animals. So if we're going to look at affordability as it affects setting an MCL, it should be focused on the cost of the water that impact public health, not the cost of water in general. So And this is my favorite statement, is that drinking water is not just about drinking water. Public uses water for many things, and a lot of those things have public health implications, even if people don't drink the water. So when we prepare food, we boil food in water, we wash food in water, we wash our clothes, we wash our dishes, we wash people, we flush our toilets. And there's a variety of industrial and commercial businesses that use water that impact public health. And the way it impacts public health is it acts as a barrier to the spread of waterborne pathogens. Now, up to this point, we've focused on chemicals because that's where MCLs are focused. But a really important part of, from a historical perspective and a current perspective, is that we are really interested in preventing the spread of waterborne pathogens. Cholera is one of the most well-known, but there's typhoid and a variety of others. So for example, clothing. Clothing is an important vehicle for the transmission of infection, and water is key to breaking the transmission of diseases through clothing. And so you can look at the slide, this is real scientific study, and said this is how diseases spread through the use of cloth and fabrics and things like that. I should say the same, you can come up with similar slides for dishes and cups and a variety of other things that act as vehicles for the transmission of waterborne pathogens and foodborne pathogens. This is a really well-known slide in the water world. The Supreme Court allowed the use of chlorine as a treatment for drinking water in 1908. And since then, the number of typhoid deaths has dropped dramatically. This is just typhoid. This isn't cholera or any other waterborne pathogen. It's a really big dramatic drop. And chlorination plays a key part of that, which costs money, of course. But actually, if you look historically, this is the curve showing infant mortality. It actually started dropping even before chlorine was being used. And what I would suggest is, part of that is the use of indoor plumbing. Before 1900, actually even before 1920, indoor plumbing was not that common. Water had to be brought in from outside. It was expensive to bring inside, difficult, and it was rather limited. So the slide here is showing deaths per 100,000 from diarrhea and enteritis, and then also deaths per 100,000 from typhoid fever. And then the blue is actually nationwide spending on enameled sanitary well. The Federal Reserve Bank keeps this data. I was able to download this stuff from the Federal Reserve Bank. And you can see there's a big increase in the use of enameled sanitary ware, really beginning in 1900, but actually really takes off about 1920. And this is in part what's driving the extension of human life and reduction in these waterborne diseases is the availability of indoor plumbing. Sorry, I went the wrong way. So typically in the past, people would go outside. This is a picture of William Mulholland, dressed as a typical waterworks employee of the 1900s. And out there's a fire hydrant, not a fire hydrant, but a water hydrant. So people would go outside, use this hydrant to get water from the mains underneath the street. So even though the water is being delivered in pipes, it doesn't actually go inside the house. This is an outdoor, and they actually go into a cistern underneath one of these hydrants. This is a steel one instead of a wooden one. Some people, well-to-do people, had cisterns inside their houses where they could pump water out. In this case, they're actually collecting rainwater, and they're passing it through a filter, and they collect it in a cistern. This is actually a map of Pasadena from 1887, and you can see this is the intersection of Colorado Boulevard and Fair Oaks. And there's hotels and banks and someone selling real estate and all kinds of stuff going on here. But as I've circled here in red, you will see all these HYD hydrants, small hydrants. So water is being brought in from the street, and you'll notice that dashed line around that, those are pipes. So there's pipes underneath the street, and then there's a smaller service pipe that goes out to these hydrants. So people can go outside and bring water into their house. None of these dwellings have indoor plumbing. This is just sort of an interesting historical curiosity. This is actually still in place. This is in South Pasadena, which used to be part of Pasadena's water system. Again, water would come through the street and it would dump into this cistern on the right, and you had this chain pump, which would bring water up. This is a shot from a report from the city of Los Angeles City School District. In 1917, every single school had bathtubs and showers because most of the students did not have those. And to prevent the spread of disease at school, and generally to improve their health, the city school district provided this. This is actually a description in the report of the fact that they are providing these. So again, it gets to the point that one of the key spread of waterborne diseases was a major issue 100 years ago, and would begin today where we're not taking all these additional precautions, and that water is the vehicle for intercepting the transmission of waterborne pathogens. And this is really, I think, a key point in our presentation, it's my presentation, is that the price of water impacts public health. Having enough water for all Californians to use, for all their different public health uses, is really important. If the water is too expensive, people will not use enough of it. The higher the cost of water, the less they will use. This means if people are not washing their clothes as much as they ought to, not washing their dishes, not washing their clothing or their children enough, this will increase the risk of spread of pathogens. So when you're setting an MCL, we're saying, okay, we're going to increase the cost of water by treating it to remove, again, I'm using Chrome 6 as an example, but it could be arsenic, it could be any other chemical you can think of, or actually any other pathogen for that matter. You are increasing the cost, which now could negatively impact the risk of waterborne pathogens because the water is too expensive. So what we should, perhaps a different approach would be to say that the MCL is affordable when the increase in the price of water due to the implementation of MCL does not impair the ability of consumers to purchase enough water to meet public health needs for a quantity of water to prevent the spread of waterborne pathogens. So right now, this is actually a big topic of discussion. The discussion is, the state has adopted a right to water, that people have a right to the minimum quantity of water. And right now they're talking about 55 gallons per day per household. And so you might say, okay, you want to set an MCL at a cost that will allow people to purchase at least 55 gallons per day. So you saw that slide earlier where we were looking at, okay, the bottom of our curve there, our x-axis down there, is an MCL for Chrome 6. And we go from 1 to 100,000 micrograms per liter. And as you go lower and lower concentration, the cost of compliance goes up. And these are completely arbitrary numbers in terms of the costs. Now, our cancer risk does indeed go down. And we could say, we can assign, at each concentration, the number of people we believe will avoid getting cancer and assign a numeric value to that. But as the MCL goes down, the price of water goes up. We now see on the blue line, which wasn't there before, the microbial risk goes up. Why? Because people are going to start being unable to afford to buy and use 55 gallons per day per household of disinfected, microbial safe water. So
Wait, is it 55? Is it 55 per household or 55 per person in the
oh,
household?
that's a good question. I forget. I think it might be per person.
Per person.
Yeah,
but I don't remember.
I read per person, but I don't know how you figure out how many people are in.
Yeah, people are agreeing sort of on the concept, but then how do you actually make that real? How do you make that something implementable? Maybe you charge a different rate for the first 55 gallons per person. You'd have to know how many people are living in each unit, each building unit. So yeah, but that's sort of the idea. So so the idea is that a possible idea is that we would say, okay, an MCL is affordable when the increase in the price of water due to the implementation of MCL doesn't impair people's ability to purchase enough water. That's this case, 55 gallons per person. That's just, and that's an arbitrary number. We'll just let's use that for the purposes of discussion. See, I'm sorry, I went the wrong direction. So maybe we want to set the MCL at this intercept rather than the other intercept. So maybe if we combine the risk, the curve might look something like this. And we look for that minimum on that curve. Make sure here. Let me go back up. I want to expand on one of the things here, since I am just a little bit ahead of schedule. And that's well, really, it's right. It's these slides right here. Is that I kind of went through these a little bit quickly. Is that we use water, drinking water, and so if we remember, we were looking at how people were dying a lot from typhoid fever, cholera, and things like that, and it wasn't necessarily that they were drinking water. These organisms can be in the food, it could be on these animals, and they can get onto surfaces. And these pathogenic organisms can in fact be spread not just strictly through drinking water, but by the application of that water to clothing, to food, to animals, which then gets into, you see here, skin, mouth, and eyes and nose. Now, if you saw that slide, which I'd shown earlier, the school district, the Los Angeles City School District, that's why they invested in these bathing facilities at every single one of their elementary schools and their high schools as well. They only had one high school at the time. Is because of all these possible health risks, and even if one student him or herself was not at risk, it could be spread from the other students. So this was a place where disease could be spread. These kinds of diseases can be spread. Now, we focus here on chlorination. It's a widely used and extremely effective technique, but it's only one of many. We have what's known as a multi-barrier approach. So our water is filtered. It's also chlorinated. Now, as I show, let's see if I go right back here. In the past, so if we go to this slide here, if you went outside, the reason we have a hydrant there is because the water is not pressurized. The water might be sitting in a reservoir somewhere and simply being fed by gravity. And depending on how much water is in your reservoir, it depends how much pressure that system can have. So even that, you can see that wooden hydrant is probably no more than 4 feet off the ground at the discharge point. Yet there isn't enough pressure to get the water to come up. You have to pump it up, which means the water in the pipe is not pressurized. So water could infiltrate into the pipe because of the lack of pressure. And this is how water could become contaminated. So you might have a fine, pure source up at your lake or up at your river, whatever your source of water is. But if it comes through the pipes and the pipes leak inward, then you're going to contaminate your water. And that's one of the big advantages of chlorination. But the other thing that's happened is we now require water to be pressurized at all times. Water has to be at least 10, I think it's 5 pounds per square inch at all times to prevent infiltration. And again, it's the same principle. We're trying to separate, sources of contamination from our water that we can use. So I think this pretty much covers what I really wanted to cover. So if there's no objections, I'll do some question and answer now.
Okay. Can I ask a question then? You see emails from folks like the Environmental Working Group, and they'll send you a message that implies that they have set their own drinking water quality standard because they don't think the ones that government has set, whether it's state or EPA, are adequate. And then they'll tell you that your drinking water is suspect because it doesn't meet their standard.
Right. And generally what they'll do is they'll look at the PHG or the MCLG and they'll say, oh, well, you know, Pasadena Water and Power water does not go all the way down to the PHG or MCL. The other thing they've done in the past anyhow is they use the raw water. So some of our wells do have various contaminants in them. We have treatment plants to remove those contaminants or treat them in some way. And so, yeah, if you look at the numbers that are beef pre-treatment in the raw water, you're going to see a fairly high number. But they actually, what don't do then is say, well, what's the actual water people drink? But the other end of this is, yeah, we'd all love to have water that has, you know, down to the PHG or MCLG. But then the question is, what's the cost? How much would that water cost? And could people afford to buy that water? Would water at that cost now prevent people from using water for other public health benefits? Again, washing, things like that. And so you may be reducing the risk, say, of cancer, but you're increasing the risk of waterborne pathogens. And so this gets back to a sort of that discussion about back with the net present value of human life. Let's take the EPA's approach, say it's $9.1 million. But so with each cancer death you avoid, you've saved $9.1 million. But now you have placed increased risk on someone else of getting typhoid or cholera. And if we wanted to go down that path, we could then assign values to those lives. So yeah, this is really the crux of the discussion with Environmental Working Group is, yeah, it would be great. Nobody's disagreeing. It would be great to have lower concentrations of these carcinogens or other, chemicals. But what's the cost? How are we benefiting one set of risks against another set of risks? I see another hand of a Roddy.
Brody,
Okay.
yes, I have three questions actually.
Okay.
You said there are, different water quality requirements for people versus plants, and I think you had three different things.
Yes.
But surely you're not proposing running three different pipes to every house in the city.
Well, no, I want to mention that because so we work in the drinking water business. We work under the Safe Drinking Water Act. The Safe Drinking Water Act, which includes all the MCLs and all the other requirements, has the sole goal of protecting human health. Now, there is something called the Clean Water Act, which covers basically all other waters. So this would include, sewage treatment, discharge of water into rivers, discharge of river water onto land. And so when they set what would be their equivalent of an MCL, they do consider, impact on fish, impact on wildlife, impact on plants. So my point was that if we were when we look at drinking water, we have to be focused on human health and not, other sorts of components. So I'll give you an example. You may have been hearing about microplastics. They discovered that, biodegradable plastics release these fibers. They get out in the environment and they can cause all kinds of problems for marine life and aquatic life. And the people are looking at possibly regulating this. And so there's that going forward. However, to date anyhow, no one's found any human health impacts from these microplastics. So it may turn out that the agencies enforcing the Clean Water Act may adopt standards for microplastics, but those same standards may not get applied to drinking water. So you had a second question?
Yes. What is your personal and the city's position relative to gray water?
Well, the city is encouraging use of green water. The water division of Water and Power has classes and to teach people how to harvest gray water. And I believe you can get take these classes, and they've actually installed demonstration projects in Pasadena where people are collecting their wash water for use in the backyards, things like that. So yeah, the city's really trying to encourage use of that kind of thing.
Okay, thank you.
Well, sure. Anne, you have your hand up?
Sorry, I always forget to unmute.
Yes.
I was curious about using potable, reused water. Is that something that you see as definitely being a huge source of water in the future for Southern California?
Well, it already is. There's two kinds of reuse. There's indirect and direct. Orange County has been taking advanced treated sewage water and injecting it into the ground for decades. Same in San Diego County. So indirect potable reuse has been around for a while. And that will continue to be used in a much larger scale. However, people are looking now more to direct potable reuse. Even as we speak in Carson, the Los Angeles County Sanitation District has their very large treatment plant right next to the 110 freeway. If you've ever driven down the harbor on the 110, you've probably seen it, maybe even smelled it. They are building a 1 million gallon per day treatment plant to take that water and turn it into potable water. So that's already in the process. What Pasadena has attempted to do in the past, and we have not yet been successful at, is to use reclaimed water for non-potable uses, for irrigation, basically, things like that. Pasadena, there's a sewage treatment plant on the LA River in Glendale. It's called the Los Angeles Glendale Water Treatment Plant. They pump that water uphill to Shoal Canyon, which is a landfill right on the border between Glendale and Pasadena. And they use it for dust control. So they spray it, keep insects down and keep dust down at the Shoal Canyon. In principle, we could take that water from that, there's a big tank up there, and run it down the hill and use it for irrigation. We've, again, have not yet been successful at trying to do that, but it's something we've talked about, and it's been out there for discussion. So that would be use of non-potable water for non-potable uses.
Thank you.
Sure. More questions?
I have another question,
Sure.
Kathy. I see a lot of people buying bottled water.
Yes.
How is bottled water regulated for drinking water quality?
It's regulated as a food product. It's a beverage. And so it is regulated under the Food and Drug Act. California has a Food and Drug branch which regulates bottled water. So it's not considered potable water, it's considered a beverage. Now, in terms of MCLs, which was sort of the topic of discussion, they have to comply with all the same MCLs that we have to comply with one exception, and I don't want to get into really a technical issue. But the difference is, no one has to drink bottled water. It's something people choose to do. Our water is delivered directly into people's houses, and they really have no other choice but to use our water. So that there's a whole different, the real big difference is on the treatment side. So all of our operators, people who operate the pumps and the wells and whatever, have to be certified. They have to take classes, they have to be trained, and they have to have a license. And the more complex the equipment they have to operate, the more complex license they have to hold. So we have distribution licenses and we have treatment licenses. We have to use laboratories that are accredited. I supervise the laboratory, and so all of our employees have to be vetted by the state, and the laboratory itself has to have a license. So those requirements is not what you get with bottled water. And the discussion I have with people on bottled water is the main reason, and they've done surveys and things like that on this. People like the taste of bottled water better than tap water. And there's a reason for that. Generally, people drink bottled water cold. People don't drink tap bottled water at room temperature if they can help it. Sometimes, you're not in a place where you get that choice. But for the most part, that's what it is. And so what happens is, for a taste and odor issue, when water is cold and you drink it, it actually shrinks the taste buds on your tongue. And so you actually can't taste the water. Cold water doesn't have any taste compared to the same water at room temperature. It's like, if you go to a winery and they tell you to, you swirl it around, you smell it, and you drink it at room temperature, because that encourages the largest amount of volatilization of the elements of wine that people want to have, the taste and the odor. Same thing happens really with bottled water. Water's cold, you shrink your taste buds, so you end up not tasting the water at all, but you do have the pleasant sensation of having cold water in your mouth, especially when you're thirsty. That's really a big positive that we really can't compete with, if we want to put it in those terms, except to the extent that people take tap water and put it in their refrigerator. Now, the other big difference is, of course, water, from the tap has been sitting in those pipes often for quite some time, and you can become stale. This is slightly off topic, but one of the most common complaints I get is that the water smells bad. It smells like rotten eggs or sewer. And it's true. And there's a chemical called hydrogen sulfide, which produces that odor. It's the rotten egg odor. And what happens is people, there's a sink. Underneath the sink, there's a gooseneck where it goes up and down like shit. There's like a gooseneck, and it's called a water trap. And there's always water in there to prevent odors from the sewer from coming back up into the house. And so we always keep water there. Well, if the water gets stagnant, there's bacteria there which will take sulfate, which is naturally occurring in the water, and reduce it to hydrogen sulfide. And then the water gets saturated with hydrogen sulfide, but it's still down in the sink, in the gooseneck. So someone comes up to the sink and they turn the water on, the water goes down and it forces up the hydrogen sulfide. And so they smell this puff of hydrogen sulfide, and they assume because they smelled it after they opened the water that's coming from the fresh water, when it's actually just the stale water underneath. So that's another thing we have to deal with, is that the water you get from the tap, especially at the first, half a liter or liter, is probably stagnant, not very stale, and maybe not be the best tasting water. But that's my 5 minutes of discussion on bottled water.
Thank you.
I have another question.
Sure.
Okay, so David,
Yes.
what has the pandemic done to the water, supplying water to people? Have there been any health implications that I don't recall anybody has ever said, watch out for the water?
Yeah, well, actually, at the very beginning, there was that discussion, and we actually put out a press release saying coronavirus is spread through the air, it doesn't go through water. So there was a brief period where people were raising that issue. The interesting thing for me anyhow, and maybe you won't find this interesting, but is years ago, I went to a conference in Milwaukee on the International Symposium on Waterborne Pathogens. And one of the things they did was they did a tour of the local sewage treatment plant. And even back then, this is 20 some years ago, they were checking the influent and effluent for the presence of viruses. And they were not the only ones doing it. And so these viruses, this is how they detect which flu virus is going to come out next year. Every year you come out with a seasonal flu virus, a flu vaccine, and they have to sort of, it's a little bit of guessing game. There's a bit of witchcraft involved in it. But by examining the sewage treatment plant, they can figure out which viruses are likely to be common in the subsequent year. And that actually can apply to the COVID virus as well. Because although, the disease itself causes, trouble with the lungs, it causes, pneumonia. The viruses are shed not just through breath, but also, through the feces. So the feces, if you have COVID, your feces will be full of COVID viruses. They're not transmittable, thankfully, in that form, but they will be there. And that's how the public health officials, Centers for Disease Control, figure out what the status is and what viruses are likely to be showing up in the future.
Is anyone doing COVID surveillance in the LA basin using sewage effluent like they are like in Australia?
I believe they are, but this is a little bit outside my area of expertise.
Yeah.
But I believe they are, and it's not just, it's a nationwide thing. It's again with viruses, they have sentinel sewage treatment plants all over the country, and they routinely monitor this, and they get reported to a central facility wherever the CDC's headquarters is. So I'm sure they're doing the same thing with COVID, and I'm sure that Southern California has a sentinel facility where they're making those examinations.
We're doing it in San Diego, and I think UCSD is running it.
There you go.
Terry has a question in the chat box.
Oh, okay. I don't think I can access the chat box right now.
I'll
So
read
you
it.
could read it for me.
I have a friend who distills all his drinking water to make it safe. He's very concerned about fluoride and other additives. Seems extreme to me. Is it really something to be concerned about in LA County?
Well, it's an interesting discussion because fluoride is been controversial for decades. In I can say for Pasadena, all of our water has fluoride in it, but it's naturally occurring. We don't add any fluoride. And there are places in California where the fluoride concentrations are so high, they actually have to remove it. Not too many places like that, but they do exist. I can say, I'll say, maybe I'm not speaking for the city in this matter, is that fluoridation has been around for a long time, and it's very effective at preventing dental decay. It's a natural component of our teeth and bones, and adding fluoride to our water strengthens our bones, strengthens our teeth, the enamel in our teeth. So the one thing that's been interesting is Pasadena Water and Power is run by pack rats. We don't throw anything away. And so if you go down to, and I don't encourage you to do this, but if you were to go down and go through our files, we have physical paper records that go back to the 1860s. And we actually have this big file downtown, all on fluoride, going back to the 1920s. And people have been opposed to fluoride, the addition of fluoride to water, since at least then, when it was first introduced. And what's interesting is there's always a constant level. People are always opposed to it. Same number of people, same percentage of people. But what changes is what they think the problem is. So if you go back, originally the concern was fluorosis. And if you drink water with very high concentration of fluoride, your teeth will turn brown. And actually your bones will turn brown too. And most people don't like that. In fact, that's how they discovered that fluoridation prevents dental caries. In Colorado Springs, Colorado, a dentist showed up. This is back in the 1880s, 1890s or something like that. And he found a town full of people with brown teeth, but he found a town full of people without any cavities. And so he started saying, well, he didn't know it was fluoride, but he knew something was going on there. And that's really what the roots go back to. And so originally back in the 20s and 30s, people were concerned that if we added fluoride, our teeth would be discolored. And so we're very careful when we add fluoride, and again, Pasadena doesn't add fluoride, to add enough that you'll get the benefits of fluoridation without this unpleasant side effects. Again, as in the case with MCLs, it's a question of balancing risks and benefits. But later, there were various concerns with it being, something a communist plot, or it was a waste product, that it would cause cancer, that it causes that it's used for mind control. So the reason people were concerned about fluoridation has changed every 10 years or so, but the level of concern and consistency of concern remains the same. Yes, please. Rhodey?
Yeah, I think you're calling on me. I just want to make a comment. You guys have been talking about purple water from Glendale for a long time.
Yes.
And I thought that you guys had approved going ahead with that, and maybe the city council as well. At least you could water Brookside Golf Course with it, and a few places that are close to Glendale. That's just a comment. My question is that PWP has a water integrated resource plan, IRP. Could you tell us when it was last updated and when it will be updated again?
Okay, just real quick on Glendale. The issue is strictly that we don't have funding. It costs a lot of money to move that water, and the city has yet to secure funding. It's a long, complicated story, a little bit of Chinatown involved. That's as far as and it's not really my area of expertise.
Okay.
The city does have an integrated resource, integrated water management plan. Yeah, I believe it's updated every 5 years. I think we just got through updating it. But we have a lot of plans, and so maybe getting that confused. But yeah, I believe it's updated every 5 years.
Thank you.
I see a bunch of hands. Are those hands current, or are those stale?
Yes.
Okay.
Do we
Linda.
just speak out? Linda? Thank you. I'm in Sacramento County, and very high water, very high in calcium and iron here. I just moved here. I am seeing that there is a lot of crud and stuff like that that goes into the dishwasher, through the refrigerator, and all of that. And in terms of talking about cost to client like I am is going to be in not necessarily personal, as far as, although I don't like it, and I feel itchy in my clothes because I wash my clothes in this water. And so anyway, how does any of the regulations on drinking water have, or does it ever have anything to do with the
Calcium and
chemicals?
magnesium.
Yeah.
Yeah, so we generally refer to calcium magnesium as hardness. The more calcium
Yes.
magnesium you have in your water, the harder the water is.
Mhm.
And it's naturally occurring. And by the way, calcium and magnesium are good for you. They are important nutrients. Calcium for your bones and teeth, and magnesium is good for your blood, your circulatory system, and your heart. With that said, yeah, people do not like scale forming on their showers and on their dishwashers and things like that. It's probably the #2 complaint in Pasadena after odors, the hydrogen sulfide odors. And in fact, Pasadena's water is kind of hard. I used to work in Santa Clarita, where they could literally make bricks with the water.
Yeah.
And why I say that is they actually, because the water was so hard, they actually put up a centralized water softening system.
Mhm.
And what they would do, the way it would work is they would increase the pH. They would add caustic soda. pH would go up, and they would add sand. And you add sand in this big mixer, and what happens is all the calcium magnesium that would normally end up on your shower stall or on your dishes settles out as little pellets, little calcium carbonate pellets, which they then could sell to people who make concrete.
Wow.
Now, this was only a pilot plant, so they didn't sell, they simply gave it away. But they did not have a waste disposal issue here, because people want those kind of pellets. It's actually an important industrial, product. And if they had expanded it, made it big enough, they could actually had enough to sell. But it is not cheap. You had to build a treatment plant, and you have to add caustic soda, and someone has to operate it. So it's, again, this is one of those cost benefit things. There's no health concern with it, but yeah, it's definitely a problem. What most people do is, on their own, in their own house, they soften their own water. And there are various companies that will provide that service to you. And there's two kinds of water softeners. There's the single pass water softener, in which case the company, and I'll just name Culligan or Rain, these are two common companies, but they're not the only ones. They will bring out a cylinder and they'll put it on your water line, and it'll remove the calcium magnesium. The process is called ion exchange. So they take calcium magnesium out, which are cations, and replace it with another cation, which would be sodium. So the amount of calcium goes down, the amount of sodium goes up.
Yeah.
Now, some people, now you can also do it yourself. There are devices you can buy at Home Depot or Osh or someplace like that, where you add your own salt and you run it yourself. Now, there's a waste stream, which you have to attach to the sewer. And again, it is something that people have to sort of decide on their own. The one thing I will note though is that because I get this call all the time. So what kind of water softener should I get? Blah blah blah. What I tell people is, I'm a chemist. So one of the most interesting things about water hardness, from my perspective, is the effect of heat on hardness. For any other mineral that I know about, and I've never heard anyone contradict this, if you have a mineral, the hotter the water is, the warmer the water is, the more you can dissolve it. So if you got a pot of cold water and a pot of hot water, you can dissolve more salt in the hot water than the cold water. Same with sugar or anything else, except for calcium carbonate. For whatever reason, the hotter the water is, the less calcium carbonate will be dissolved. And so really, the problem with hard water is the hot water. It shows up in the shower stall because you use hot water there. It shows up on your dishes, you wash your dishes with hot water. So what I tell people is, what you may want to think about, just soften your hot water. Use a lot less salt, and you extend the life of your water softener if you buy your own, or you have the company come out less often if you just soften your hot water.
Okay.
So there's a little bit of experience there on hard water issues.
Thank you.
We have a question in the chat box.
Okay.
What do you think about reverse osmosis water?
Well, again, it's reverse osmosis is a wonderful technology. What it basically does is filter everything out of the water. So it'll filter out calcium, magnesium, iron, anything you can think of. It will be literally filtered out. It produces a waste stream. Typically, 15-20% of your water will be wasted. When you remove all those minerals, they have to go somewhere, and they have to go into a waste stream, and that waste stream goes into the sewer. Now, in Santa Clarita, you can't use these devices because that's all a bunch of salt. I'm sorry, they can use a reverse osmosis, but you can't use water softeners. So you end up taking a bunch of extra salt to their system up there. But if that's what you want, then it's great. Now, they gotta remember you have reduced pressure. The reason it works is because you put a lot of pressure and you literally force water through a filter, and the stuff that gets left behind is what gets wasted. And so the water pressure will be reduced. So if you use a water reverse osmosis unit, you'll get water that's very free of minerals, but it'll be much lower pressure.
David,
Yes.
isn't RO and distilled water, aren't they bad for you to drink?
I've heard that story, but no, it doesn't make any difference. It's not harmful at all. Some people are concerned that you will be leaching out the minerals in your bones and your teeth because the water is so free of minerals. But that's just not how it works.
Really? But you can't put that water in a pipe without it.
It could become more corrosive, it's true. Not plastic pipes, but if you had an iron pipe or a lead pipe, yeah, it would definitely increase the corrosivity of the water. But that's not how it applies to human beings. Doesn't work the same way. So I see a hand up from Linda, and then Kitty. Let's go with Kitty. Or is your hand still up, Kitty?
Yes, it is. So I just want to be clear. I have RO actually. As an aside, I have an RO system, and I do not waste the water. It comes out into a bucket,
Okay.
and I use it for plants or for flushing the toilet. But
Okay.
anyway, I just wondered, is the reason to get RO then is probably not for health or anything, it's just for taste. Is that taste really different, or am I just imagining it? If I put my tap water into the fridge like you're suggesting, would it taste the same, or what's the purpose of getting RO? And then secondly, what's the purpose of a Brita or any of those types of things?
Oh, that's
It
actually,
just
we're
taste
at three
or what?
questions now. I'm gonna start with Brita.
Okay.
Brita uses carbon, granulated activated carbon. And carbon will remove things that RO will not, mainly the organic components. So if your water has some organic materials in it, the carbon will remove that. Now, the trick with using carbon is, and it's terrific stuff. I'm a big fan of carbon, but you have to replace the carbon on a regular basis. And so what most people do is when they get these, they don't necessarily keep the carbon fresh. If you know, I'm also a microbiologist, and well, as microbiologists, we occasionally want to intentionally grow bacteria. Well, there's nothing bacteria like to grow bomb better than carbon. It's just it's Disneyland for bacteria, and so they will reproduce and grow just wonderfully on carbon. And so if you don't keep your carbon fresh, you will have bacterial growth on it. So that's one. RO in terms of taste. Soft water does taste different from hard water, there's no doubt about it. Now, whether you like the taste or not, that's an entirely subjective matter. But I'll tell you a story, and what I've discovered over the years is people like the taste of water that they're used to. Once they get used to a certain taste, they don't want to change it. So if you like hard water, you're not going to like soft water. If you like soft water, you're used to soft water, you're not going to like hard water. We use, earlier we did a discussion about chlorine, and typically water systems either use what's called free chlorine or chloramines. In case of chloramines, you add ammonia to the chlorine. They taste different. So what the water utilities often do, I shouldn't say typically, but often do, is go back and forth. Free chlorine is a much more powerful disinfectant. It really does a better job of keeping those bacteria dead. But there's drawbacks. Again, it's a balancing issue. So they will run 9 months out of the year with chloramines and 3 months out of the year free chlorine. Well, when you go from chloramines to free chlorine, people will call and complain. Water tastes different. I don't like it. What did you do to the water? Well, then 3 months later, when they switch back, the same people call and complain. I don't like what you did to the water. It doesn't taste the same anymore. The biggest thing with water is people, unless it has hydrogen sulfide or something really nasty in it, people like the water they're used to. Once they get used to a certain kind of water, they just want to stick with that. So, if some people grew up in an area where the water's real soft, they're not used to hard water, yeah, they're gonna probably not like it. But once they drink it for a while, they got used to it, and then they'll dislike drinking soft water again. So I thought there's a third question there. And I'm sorry, I lost track of it. Yeah.
Why do you switch between free chlorine and chloramines?
We don't, Pasadena doesn't, and Metropolitan Water District doesn't. But the problem with chloramines is because it doesn't do a great job of keeping the bacteria in check, not as good a job, you can get bacterial growth in your system. And so particularly bacteria that like consuming ammonia. Ammonia is food bacteria like, and when you add chloramines, these bugs do get that ammonia, they will grow. So what they do is so every 3 months, it might be once a year for 1 month or 2 months, 3 months, is you give them the hard stuff, free chlorine, get the bacteria out of there, and then for the next 9 months you can go back to chloramines.
That's interesting.
All right, it's 8:12.
Can I ask one more question?
Yeah, sure.
You talked earlier about how people will get that hydrogen sulfide smell because of the bend in their water pipe.
Yeah, the gooseneck underneath the sink.
The gooseneck.
Very
If
common.
Water's got a disinfectant residual. How do they get the bacteria growing in their pipe?
Well, the bacteria residual does not last forever. It will dissipate on its own. So you add chlorine. So one of the advantages of chloramines is they last a long time, whereas free chlorine has a short lifespan. So it's more powerful, but because it's more powerful, doesn't last as long. And usually this will happen, like people go on vacation and they come back, they haven't been there for a week or two, and the water's had a chance to get stagnant. But if you're washing your dishes every day, or washing your hair every day or whatever, you keep that water fresh underneath there. That will usually take care of that. So it's usually a problem with stagnation. And just so you know, the solution is actually fairly simple. If you don't want to just wait it out, you pour some bleach, a cup of bleach down there, let it sit for 30 minutes, an hour, flush it out. That's happened in my house upstairs in the bathroom. Sometimes it may not be a lot, but hydrogen sulfide is super powerful. It's your nose is really well attuned to smelling it.
So this
So even if
is,
it's a tiny amount, you'll notice it. So a little bleach goes a long way.
this is in the drain pipe, not the
Yes.
water line.
Yeah, but the illusion is that you only smell it. The hydrogen sulfide is very heavy. It's very dense. And so it won't leave the pipe unless you force it out. So when you turn the water on, the water goes down the sink and forces the hydrogen sulfide out of the sink.
Does anyone else have any questions?
Thank you very much. It
Yes,
was
I'm sorry. I
really
actually I
fascinating.
realized I had gone through those slides a little more quickly than I had anticipated. But I think we ended up with a pretty good discussion nonetheless.
Yes, it was very interesting. We appreciate your spending some time with us this evening.
My pleasure. Now I have to go eat dinner because I haven't eaten yet.
Thank you so much.
Good.
My pleasure. So,
Yeah, thank
Thank
you.
you. It was so
hold on.